So on our first problem up here, ooh, we have a figure. The figure shows the resulting pattern when a single slit is illuminated by monochromatic light. That would be one color light. Slit is, so our slit width, oh hey, to draw on there. The slit width is 0.3 times 10 to the negative third, which is 0.123 meters. And our wavelength of light is 506 nanometers, which is 506 times 10 to the negative 9 meters. The distance, the diffraction pattern seen on the screen is 2.8 meters from the screen. So that's our L value, 2.8 meters. What is the linear distance on the screen between the first two diffraction minima on either side of the central diffraction max? So what they just asked you is, how wide is this thing? Ask me how wide the central bright maximum is, okay? So we have a formula for that. So there's two ways you can work this problem. Way number one is to use the formula we've given you. And I'm going to go back through how you get this. So let me come back over here to share this. So let me show you where this comes from real quick. You probably remember that W over 2 sine theta. When we do dark fringes, this is how we start. So the 2's cancel out. We get wavelength. Thin that out a bit. Then we use our small angle approximation so that the wavelength is lambda over W. Okay? So when we do that, then our next step is you count them just by the whole numbers. So for example, second dark fringe is 2 wavelengths over omega. Third dark fringe is 3 wavelengths over omega. Fourth dark fringe, yada, 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 m wavelengths over W. Not omega, sorry, I was doing rotational kinematics with AP Physics 1. So W is omega and W is width. I also put thermodynamics questions in the Physics 1 homework when we're studying gravity. So clearly, one of the kids was like, Miss Wilson, are we doing both of these? Is there like, should I watch the video to see how thermodynamics connects to gravitational orbits? Ooh, sorry about that. Wrong Physics 1 class. Standard Physics 1. So we're going to count by whole numbers. This is just a review of what we've done. And then in addition to that, we have this part that we're looking at. And here's what we're looking at. Here's our central bright. Here's the exact middle of our slit. So I'll sort of expand that to make it a little bit more obnoxious. So if I have a wavelength here, and this wavelength over here, and this is my first dark, the triangle that I need to be working with is this triangle. Here to here. So if I'm working with the screen, I usually mark this as where my y equals 0 would be the center of the slit. And then these would be positive y's, and these down here would be negative y's, just like regular math. So this triangle that we've just made, if you look at your variables, y over L, here's my angle, y over L equals the tangent of the angle. But by this small angle approximation, once again, we get y over L equals theta, which means that you can write your angle in either one of those two ways. Thank you so much. Nobody's using photocopiers anymore, so we all have plenty of copies left. So it doesn't matter which way you call theta. You can call it from the fringes, or you can call it from the locations on the screen. So far, so good? So on this problem, to go back to what we were doing, put that down, stop that share. Let's go back to this share. I'm going to use the fact that I want this width. So that's I got to go y up and I've got to go y down. So y is going to be L times theta. So that's L times lambda over W. And then at the end, I'm going to multiply it by 2 because it's twice as wide. So this piece I know. The wavelength I know. And my width of my slit is 0.3 times 10 to the negative third. And we have our answer over here, so I'm not super worried about that. This comes out to be 4.7 times 10 to the negative third. So you get, when you double it, this is your width of your central bright is 9.4 times 10 to the negative third. Now let's stop there and see if there's any questions on any of that that I just did, other than you just need to know which formulas to use at this point, or where I got everybody, because I've done that now 2 or 3 times, so I just want to make sure we're kind of okay. How to use the formulas. Yes or no, or kind of okay? How was the homework? The 28 through 32 particularly? Figured it out? Yeah, it does, and it takes some practice. What you'll find is that with the vast majority of single slit, we're working with things around that central bright maximum. Because the central bright maximum is the one that you see clearly with single slit. And of course, the bigger the slit, the more the central bright maximum gets brighter and the other ones start to fade out. So as you have a wider and wider slit, the central bright maximum gets to be a nice big clear rectangle instead of being an interference pattern with a bright and dim and bright and dim and bright and dim. Because once you get to a big slit, you only have the square of light behind the slit. You don't have diffraction exactly, you just have the light that you see. Just like with the square that I have up there that allows the projector light to be shined on the screen, you'll notice all the edges on the screen are very clean. They're very crisp. You know what I mean by that? Like you see the line, you don't see fuzzy little lines in your outline. That's because the slit is very big, so the wavelengths of light don't diffract. You don't get that fuzzy bending piece on the edges. That's what you see when you get out of focus, actually. There's a little bit of the diffraction pattern on the fuzzy piece. Okay, so let's ask this question. Not that question. Let's just ask this question, since then I'll work this next one. If I make the slit get smaller, what happens to the width of the interference pattern? The width of the central bright, or the width of the interference pattern? As you make the slit get narrower, the width of the pattern gets wider. As you make the slit get wider, the interference pattern collapses to just one big bright. Okay, so the more you squeeze light, the more it spreads out. That's usually the phrase we use for that. Okay, so let's look at this one just to get one more of these, and then we'll do some more with the diffraction, the double slit and diffraction gratings. So single thin slit forms a diffraction pattern by the first minimum is at an angle of 40 degrees from the central. Now can I use my small angle approximation for a 40-degree angle? You should not use the small angle approximation here. So what you're going to have to do is actually do W over 2 sine of theta is going to be equal to 1/2 wavelength. So this is our first situation, because what I need to find is the slit width. So I'm going to do that. W over 2 sine of 40 equals 1/2 of 410 times 10 to the negative 9th. So that would be, the halves cancel out. I don't know what the sine of 40 is right offhand. Come on, little friend. Sine of 40 is 0.6427. So 6428. Divide clear. 410 e negative 9 divided by 0.6428 is 6.38 times 10 to the negative 7th meters. So there's my slit width. The second part, they say the same slit, when illuminated by a new light source, produces a diffraction pattern with a second minimum at 60 degrees. Okay, so how do we do the second minimum this time? Well, we do our, just going to skip to the end here. What happened when we did this? We ended up with W lambda over W. So now we've got 2 lambda over W. If it had said the third one, I'd do 3 lambda over W and so forth and so on. So sine of 60 is going to equal 2, wavelength I don't know, slit width was 6.38 times 10 to the negative 7th. So now I'm going to solve for the wavelength. So 2 wavelengths equals sine of 60, 0.8660, 6.38 e negative 7. And then I'm going to divide that by 2. So 5.53 to the negative 7th divided by 2. So my wavelength is 276 nanometers, which is answer A. Which they told me it was answer A, so good. It's always good when you work the problems correctly. So you guys feel pretty comfortable with what goes where? Think so? Okay. All right, so then here's the good news. When we start doing double slit, same stuff all over again. Okay? So what changes? So first of all, let's draw some pictures so you can see what changes. So I will need a new screen piece. So let's do it like this. Single slit. And we'll talk about all the things that you can change. So here's going to be my axis. That was actually a pretty good line, but just for argument's sake. 1, 2, 3. And let me label these. Why did I write all those words? Okay. single, double, grating. A grating like a grate, you know, like a grate in the ground that has the slots where water can go into. This is multiple slits. So a single slit, let me draw these. Okay, so no draw. Thank you. Single. So here's going to be our central bright, central bright, central bright. Oh, we don't have one. That's the first difference. Single and double slit both have a central bright maximum. Gratings do not. Okay? I'll explain why that happens in a minute. Secondly, on the central bright, when we have our interference pattern, let's give myself some room to play here. 2, 3, 1, 2, 3. Just giving some tick marks so you can see how I'm scaling things and what happens on the scalings. Okay, so orange light. We'll do orange light today. So we see a wide central bright, and then we see a smaller peak, and then we see tinker out, peter out. Okay, that would be what we would see, and here's what we'd actually sort of, as we're doing this, we would see very, very dark in here, and then it kind of gets to be a lighter on the two edges. So I guess maybe the better way to draw that would be so it gets really dark in the middle. And on the edges, you just have light shading on the sides, okay? And then these two are noticeably dimmer with your ever popular black swatches. Okay, so to show this with, and we've shown it as bars, but let me show it with bars just on this top one so you can get a feel for it. We would see this, and then we would see that. And I don't care if you don't have to feel obligated to draw any of this. This is just to get you an idea. So that you can kind of match the intensity pattern below with the one that would actually be showing the light. Okay, so that's what you'd see there, okay? What do we see with a double slit diffraction? Okay, typically, your peak is going to, oh, that's not a peak. That's not a let me draw with my little hands. Okay, so right here, right there. Okay, so get so within the bounds of, you need something? Oh, you're fine. Okay. I don't know. Anybody have a phone charger for her? It's all good. Life happens. So we see this, okay? These two would be sort of our, make my pen a little bit larger now. These two would be our dim spots up here. And then you get to your first dark, right? Your first real dark, And then you get another pretty noticeable one. You're going to flatten out. Then you're going to get another one. And these are going to have many more. It's hard to do this symmetric. So forgive that. So our double slit, where this one occurs, and this is, like I said, you might want to watch rather than draw right this minute. So the next little peak here actually consists of a couple of little side guys beside him, where it's partially constructive and partially destructive. So these peaks have little peaks inside them. Okay, but they look to us just like dimmer bands. And then the exact middle, in the exact middle of that band, you're going to see one big bright strip, one big bright strip. That's your perfectly constructive. And the rest of it to the sides is dimmer. And then you get dimmer and dimmer and dimmer as you move out. Kind of okay with that? And I'll go back and show you some pictures of that here in just a second. Let me get this guy back. Come back over here. Behave yourself. Now, what happens with the diffraction grating? A diffraction grating is hundreds of slits. Maybe 100 slits in a millimeter. Maybe 300 slits in a millimeter. Really lots of slits. So what happens is this behavior gets even more extreme. And here's what I mean by that. What you really see, get thickness, give me line tool, is this. And everything else is so we've got bar, flat, bar, flat, bar, bar. Okay? These are equally spaced. So are these. This one is not evenly spaced. These is where you're going to see some fuzz on the doubles, but on the diffraction gratings, you're going to get bright, sharp lines. And it's because there's so many lights. It acts like 100 light sources if there's 100 slits. So now you have a lot more light to interfere, so they don't get as dim. They're dimmer. You'll notice what should happen on this is this peak is higher than single. It's higher than, it's lower than single. No, it's higher than single. I said that right. Higher than single slit. But also higher than grating. And so what we've got changing is not the geometry. The geometry is going to be the same geometry we were just doing. It's the way it looks on a screen, really, that's going to be the bigger difference. So why does the center bright get higher on a double slit than it does on a single slit? Well, because there's only one light source. And that light, some of that light from the central bright is now being shown out on the sides. You've got enough of the light interfering out here, but it's really acting like there's just one light bulb. A double slit really truly acts like they are two separate light bulbs. So your pool of energy is bigger. So your light peak in the middle gets brighter because it's like there are two light bulbs, each contributing their own light. But then the peaks on the sides also stay higher because now it's like there's two separate light bulbs. So the overall peak of the graph has actually gotten larger all the way across. Diffraction gratings, though, it's like there's hundreds of slits, but since they're all spread out, the slit over here, the light from this guy doesn't reach over here, and the light from this guy doesn't reach over there. So you get them overall dimmer, but they're all the same height because they're all getting equal amounts of light from all the light bulbs, sort of. So let me show you this on a image from the, there's our textbook, so I don't want to mess that one up in case somebody needs book questions posted. Okay, diffraction, gratings, diffraction, interference patterns. And then I should have put images because, yeah. Okay, so where was the good one? See all images. There's a really good one. Here we go. This is the one I was looking for. This is a book image. Take me there. So you can see that with the single slit, are they all centered in the same spot? Yes. But what do you see about the double slit compared to the single slit? Now I see several little peaks within that main peak. So your width, the width of the pattern didn't change because you didn't change your slit width. But now your overall amount of light is bigger, sort of. And when you start getting these bright and dark, that's where you get the peaks starting to dim out. The diffraction grating is going to look much more like this one at the bottom, just a whole bunch of peaks that they're exact same size. Yes or no, or kind of okay. How could we make the peak overall taller? What would we have to do to make the peak of this taller? What is this a graph of? It's a graph of intensity, brightness. So the only way to make the peak get taller or shorter is to brighter, dimmer light bulb. So you use 100 watt instead of a 60 watt. Use 120 watt instead of a 100 watt. That's what controls the vertical height, is the amount of power or the energy being put out. But then the slit patterns are dependent on how many slits you have. You have a lot more interference pattern combining going on to make the peak for the double slit because it's acting like two light bulbs. When you get to the triple or the diffraction grating, it's like hundreds of little lights all combining their light. But realize it's still only one light source, but it acts as though there were 100 light sources, just 100 dimmer ones, if you will. So let's go back to look at one more picture from there. Okay, I need you. Bye-bye. So let's show you some diffraction. Some of you have heard of, let's see, this is electromagnetography. This is the thermal. This is the thermal electromagnet. So if you want to look at materials and want to see where things get hotter or cooler, you can actually use thermal imaging using diffraction, because as we heat these up, they start giving off energy, right? And you can see that some particles give off different amounts of energy. So you get, because of the diffraction nature, heat is light, heat energy is infrared light. You can use that to image something to see where the heat is catching up. So like if Ethan was going to build a new computer for himself and he wanted to see why the heat sink is failing, he could see if there's a location in there that's not like it needs to be. Or in your body, what would heat usually indicate in your body? If your body has a really hot spot, what does that sort of indicate?
High blood pressure.
Could be high blood pressure.
Fever.
Inflammation.
Could be inflammation.
Infection.
Can be an infection. So something, your body signals something's not right with heat. A fever, of course, would indicate that somewhere it's a systemic sort of problem, not just in a location. So we can use this to do imaging, and you may notice these are tiny, but these are actually little pieces of, I'm wondering what that is. These are probably, looks like a heat sink sort of. And these are 200 nanometers. So they've been zoomed up 1 billion times. This is 1 billion times larger than it is in real life. Isn't that crazy? Like 1 billion is hard to even think about. Because nanometers is, I'd have to actually do the calculations for the imaging, but we were just saying you can see where breaks occur because of where the edges are. Yeah. So you can see the fringes that tell you a little bit about the structure in here. It's kind of crazy though. So if you're using this for body imaging, tomography, tomography is an interesting little animal. But I was trying to see if they had any with a Fresnel lens, just so you know, if you've ever heard of a Fresnel lens, these are the lenses that go in lighthouses. You know, the big windows in front of the light source is a Fresnel lens. So what they do is they make it into essentially a refractive grating. So it has these slits in it, which focuses that light beam as it sweeps across the ocean. So they're using diffraction to combine the waves. It's kind of cool stuff. Okay, so all kinds of cells and cores and things that we could play with. Okay, let's see. I think that's kind of what I wanted to do with that. So now let's get into the math part of it. You can look at some more images. Yes? Oh, okay. Yeah. Oh, sorry. Sorry, people online. I did not share that with you, did I? I'll come back to it. I will come back to that. Let's do the math part and then I'll come back to that part. Okay, so let's math it up for a little bit. We've already gone back and done this sort of, I'm going to give you the quick review of the argument here. And the quick review of the argument when we were doing single slit looks like this. So what happens when we go to 2 slits? What really happens? Well, let's do that. Does anything about our geometry really change? Well, now we've got two slits, right? But we're still going to have this. Here's point P, 1 photon from there and 1 photon from here. So guess what our math does? Same exact thing. So if we do, we don't have to trick it into being 2 slits now. We just have to treat it like 1. So our slit widths are actually going to be D. We're going to use the letter D for slit separation now. So instead of treating it as half widths, we're going to treat it as slit separation. Where with a single slit, what we were really doing was measure this width and then take it and cut it in half. You've already got that here. Your slit width is from the top of one to the top of the bottom, right? Like if I wanted to measure it from here to here, or measure from here to here, or measure from this point to this point, I want to keep that consistent. So it's my slit separation. So what does that change about your math? That's about it. So what does our math look like? Well, let's see. When we did dark fringes, Wilson, what are you doing? Not so fat. Bright fringes. With double slit and diffraction gratings, we tend to work more with the bright fringes. With single slit, we tend to work more with the dark fringes. So let's just go ahead and see what this does. This is going to turn into d sine theta equals a wavelength, or d sine theta equals 2 wavelengths, or d sine theta equals 3 wavelengths. You see how we're counting? This is y equals 0. So d sine theta equals a number times the wavelength. So what happens to your dark fringes? When do you get a dark fringe? Wavelength over 2. Three wavelengths over 2. 5 half wavelengths, so forth and so on. Everybody see what we're doing? It's identical to what we just did, yes, with single slit. So what's the only difference? The difference is we use D to remind us that we're doing the distance between slits, not the width of the opening. So single slits, you're working with the width of the opening. Double slits, you're working with the distance from one slit to another. Okay? That's the first part. Now, how do we count? Because what we want to be able to do is count so that when we're working problems, if I use M is 4, then I know M is 4 for bright fringes and M is 4 for dark fringes, and I don't have to guess. Does that make sense? In other words, the fourth dark fringe, I want it to mean the same thing as the fourth bright fringe. I just put in a 4 for my number. So to do that, what we've had to do, because we need to get those odd wavelengths, right? You guys may remember we had to get, with double slits, we've got to have the odd wavelengths. So here's what happens. This part turns into d theta equals m lambda with small angles. Okay? When we're doing the dark fringes, we're going to have to remember that it's going to be, if you like, we do d theta. So we want to make these odd, right? So to make these odd, how am I going to turn this into an odd number every time? If this is 1, 2, 3, 4, I want this to be first, second, third, fourth. We do 2 times m minus 1. So the third one is 6 minus 1, 5 halves. The second one is 4 minus 1, 3 halves. The first one is 2 minus 1, 1 half. Do you see how this piece makes the dark fringes count 1, 2, 3, 4, but it gets you the right half wavelength that you need to be on? So here's our bright and our dark. Here's our bright and our dark formulas. So what happens to the central bright now? Because that's another thing they like to ask about. What is the width? Here, let's do this. More space over here. What is the width of the CB? What's the width of the central bright? Well, what we do is on this case, we don't usually find this. We know that the fringe spacing is equidistant. Fringe spacings are even in size. So the way we get that is we get, if you'll recall, from here's our triangle, there's our L, there's our Y, here's our triangle. So if I want to get to the next one, if this is say 3 centimeters, the next one up here will be 3 centimeters. The next one will be 3 centimeters. The fringe spacing is even. So what we actually use here is lambda times L over your angle. Or the more common one is lambda L over your separations piece. So let me hit this real quick. Sorry. So y over L equals tangent of theta. So then we just do y over L equals theta. You may remember that. But we also do from here, d theta equals 1 ml. So d theta equals L. So d equals L over theta. So y is going to be L theta. And you can substitute between these two depending on do you want the wavelength or do you want the angle. It's the same math we did last time. Okay? So you can do it with the D or the theta. Either way is fine. The more common one is the one with the slit separation though. Okay? And then last but not least, what do we do with diffraction gratings? What do we do with diffraction gratings? Here we go. Diffraction gratings look like this. You have lots of slits. And what they usually tell you with the diffraction grating is this: 100 slits per millimeter. So we're still going to be using d sine theta equals m lambda. D sine theta equals 2m minus 1 times theta over 2. And y equals L theta over WD, or L, sorry, we don't have a central bright on this one. That's the one where it's going back to single slit. No central bright. This one has no central bright because they're all even. So we just have dark and bright, but usually what we have to do is this. We have to find D first. So D is the slit separation. How would we figure that out if there's 100 slits per millimeter? What would you need to do to find your slit separation? One millimeter divided into 100 parts. This would be your 2. That would be your D that we use here. What if we have 300 slits per millimeter? Then you'd have D is 1 millimeter divided by 300. So we get 3 times 10, or 3 times 10 to the negative 6th on that one. And that's your D value. So the math is exactly the same for double slits and diffraction gratings. They're exactly the same. it's the only thing you have to do is you have to figure out the slit separation. And that's a pretty easy calculation. Okay? All right, so I'm going to stop there. And I'm going to post, I'm going to, distance learning people, I'm fixing to put that picture you couldn't see up. I'll put that back up and talk about it. Physical in-person people are fixing to get these handouts. I'm going to upload these to you guys this afternoon because I have to scan them. So this one and this one. Here's fraction gratings. Here's regular diffraction. Diffraction gratings and regular diffraction. One of these for you. Okay. So you guys are going to have the rest of the time to work on these in class. Yep.
So where am I going to put my double link from Wednesday?
Yeah, just put it in the green folder up here.
With the turning slide?
Yep. So you guys, anything you want to turn in paper copies of, you can just hand them to me. Okay, so Physics 2 online, folks. You're going to have the rest of the time, but let me go back through those pictures so you can see them a little bit. And I really apologize for not recognizing that I hadn't shared them to everybody. So let's go. Okay, so let's share this. So for my people, you guys that couldn't see this before, here's what we're arguing at the beginning. And I'm gonna, hopefully you can see that now. So on a single slit, you see one big peak that fades out. On a double slit, you get the main peak, but the main peak is actually composed of several smaller peaks. So you get sort of the same looking pattern, but for different reasons. In the double slit, you get more of the wavelengths of light, like 1 wavelength, 2 wavelength, 3 wavelengths. You see those as individual, so they get squished into the same space as the single slit, but you get many more peaks. So you see more peaks in the same space. The height of the peak is the same for both. But if you go to a diffraction grating, let me disconnect this real quick and turn this off. So hopefully they'll disconnect. So when you go to a diffraction grating, here's what happens. Just to contrast. So if you saw a double slit diffraction, the brightness and lightness pattern would look like this, where the double slit would have sort of several little chunks that all blend into one. You get one clean one with single slit. You get lots of itty bitty ones. But your double slit has peaks at the same locations that your single slits do. You just get multiple peaks inside each individual peak, if that kind of helps. Then last but not least, what does a diffraction grating look like? Can you get off my screen? Okay. So now let's look at comparison of diffraction grating with the single and double slit. So when you go to diffraction grating, it's going to look more like this. So the front one is your double slit. Notice all the peaks are the same size, but with the single slit, When you get the single slit, it's a taller one than the double slit because you've had to spread the light out a little bit more. The double slit has more peaks within its main peak. So its overall height has decreased, but the peaks on the sides get a little bit bigger. So you have less in the middle and more on the sides. Single gives you almost all in the middle and few on the sides. And then a diffraction grating gives you very clean, bright lines so that all you see is red, 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 red. They're all equal in height, just about. They're about equal in height, and they're equally spaced. So you get equal spaced ones on double slit, you get equal spaced ones on diffraction gratings, you get more space on a single slit. And so that should help you a little bit. So if we go back and look at some more pictures of that, you can see what's going to happen. When we go from one slit to two slits, just get over to that image if I can. So there we go. So what you see is the single slits at the top. The double slit looks like it has 5 peaks within the one original because it does. And then you get, as you add more slits, this is 3 slits, 4 slits, 5 slits, 6 slits. You'll notice that by the time you get to 6 or 7, they all start to look about the same. But what ends up happening is this central bright starts to spread out. And when you have hundreds of slits, then they're all equally bright or equally dim, depending on how you want to think about that. And they're all equally spaced. So those were the images I was showing you, and I'm really sorry I didn't catch that you weren't seeing them initially. So now I'm going to stop sharing that, but I'm going to hang out here for the next, next minute, the bell's going to ring for us to do lunch, but I'll be in this, in this area so that if you want to come in and do some review questions about like one of the AP review quizzes, that's the time to do it is Throwback Thursday. It's today. And then the rest of class, you can use what you need to.